In this lecture, we will learn about processing of bioceramics, because in earlier lectures we have seen what kind of ceramics do exist, what are their natures in terms of their inertness, bioactivity or bioreabsorptionness. So in this particular lecture, we will learn about the processing of bioceramics. First is thermal processing. So in thermal processing, there are many kinds of microstructures which we can really get. So we can see we can either achieve amorphous or glassy kind of a microstructure, or it can also be cast or plasma sprayed structure. We can also do this processing via liquid phase sintering. We can also perform solid state sintering, and we can also achieve sometimes polycrystalline glass ceramics. It can be again glass in glass, or it can be glass to ceramic kind of a microstructure. So we can see that via thermal processing we can attain different kinds of microstructures. It can range from being structure being very amorphous or glassy. It can also be polycrystalline, which can be achieved via casting or even by plasma sprayed structure. It can also be liquid phase sintered, in which we can attain really very high density of materials, or it can also be solid state sintered, wherein we don't allow one material to undergo any liquid phase transition, or it doesn't allow to go to liquid phase, and then we attain the sintering via just particle contact, and then we can also get polycrystalline glass ceramic via certain processing techniques. So first technique of thermal spraying is sintering. In sintering, what we are doing, we take a fine grained particulate and then we add some water and some binder to it, so that all the particles which are out there, they can get bound together, and then we press them in the mold. After pressing, we get approximately near net kind of a shape, and then it is called a green. So green is attained once we take our particulate material, we add water, we add binder, and then we press it to approximate near net shape, and that is called a green. Again, it will have certain porosity in it, and then what we do, we take this particular green and we heat treat it, so that the first step is that we evaporate water from here. So once you are evaporating water, then we have something still remaining. There is some binder also remaining therein. So we have a kind of a green which has been pressed component, which is again which will also have certain porosity into it. So first step, we are trying to evaporate the water from there, and then we heat it to further higher temperature, and that basically burns the binder. So now our overall billet or whatever the component is, it is free from water, it is free from binder, and then we now sinter it at very high temperatures, which leads to the densification. And once we have attained a particular densified composite, we can polish it to the final requirements. So in this particular case of sintering, we first take fine granulates, we add certain binder and water, so that it can basically bring out all the particles together because of capillarity. And then first step is that we remove the water. So we will have all the particulates, and then water will basically get evaporated, and then in the next step we will burn the binder which is still holding the particles. So it is some sort of organic binder, and then we burn off the binder which can burn out at pretty low temperatures, order of 300 to 500 degrees centigrade, and then we basically sinter it at very high temperatures, which can be exceeding 0.5 times the melting temperature. So in that particular case, we now start seeing all the crystallites which are belonging to a particular biocomposite, bioceramic, they tend to start sintering together, and then we can achieve a more densified structure. And then once we have a particular component, say if we have a particular component, it can be polished, so that we can achieve a near net shape with a good surface finish. So these are all the processes which are required in the sintering process. That first of all, we have particulate, we add water, we add binder, so that now we have a we have particulates which are basically kind of accumulated together because of capillarity, and then we basically then compact it to produce a green. Then we remove the water from it or dehydrate it. Then we burn off the binder at certain temperature. Then we basically sinter it at much higher temperature, exceeding 0.5 times the melting temperature. Then after we have consolidated it, we have densified it, we will basically polish it to our finished size. And in second case, we can also achieve something called porous ceramics. And in porous ceramics, how do we get it? First of all, we will mix two-phase material, and we provide a controlled heating and with a controlled environment. So we have initially two phases, one phase and second phase out here. So we will have one phase, we have second phase, which is basically being embedded into the two-phase material, and we provide controlled heating with controlled environment. So what happens? We allow the decomposition of the second phase before densification. So what we are doing is we are basically removing the one of the components. So what we are doing like this, it's more like this, that we take a particular component, and in second case what we are doing, we basically burn off the second phase. So we remain with only first phase material, whereas second phase material has been decomposed. So it will leave out certain porosity at its place. So this was phase 2, which is now basically burned off. So this was phase 2, this is phase 1, and now the phase 2 is basically being removed, or it has been decomposed. So we have overall composite with certain porosity in it. So that is what that leaves the porosity behind. Or we can also do, we can have phase 1 and we can have phase 2, but in case of this, in this particular case, we can let the second phase transform to hydroxyapatite. So what we are doing, we are taking some natural porous organisms, such as which can be coral. It already has certain porosity into it. So corals will have definite some porosity inside them, which can it can vary from size, or to it can vary from the size of the porosity to their connectivity, but they will have very good porosity, interconnect porosity with certain pore size. And our objective in the second case is that we convert that particular coral to certain hydroxyapatite by certain hydrothermal processing. So it is we take the particular calcium carbonate or any phase of calcium phosphate, and then we make it react with water or certain chemicals, so that that particular phase converts to hydroxyapatite, and that will produce eventually a porous ceramic. So here we are basically trying out two methodologies. In first case, we are mixing two phase material, and then overall what we are trying to do, we are trying with the controlled heating and the providing a particular environment, we are letting one of the phases get decomposed. And since one of the phases gets decomposed, the second phase remains continuous, and the phase 1 which was decomposed leaves porosity behind itself. So we are getting overall a controlled porosity which equals to the amount of phase 1 which is present, and then phase 2 forms a continuous network of the required implant. So implant material. So that is what we are doing in first case, and in second case we can take a porous organism itself, just which can be coral, and then basically we hydrothermally process it to hydroxyapatite to leave again a porous biocompatible material. And third process can also be casting, and in this particular case we can take silica, which is SiO2, and SiO2 is a network forming oxide. So silicon oxide basically tends to form network with itself, so it may not lead to a very ordered or crystalline structure. It will basically start forming networks. So network means it will just link onto the other silicon oxide, and it will keep growing in that particular manner without any particular type of arrangement to it. And what we can do, we can add also something called network modifier, which can basically associate itself to the network and get attached to it. So that can be calcium oxide. So we get a kind of a mixture between the silicon oxide and the calcium oxide, and in this process we heat them to the melting temperature. So in this particular case we are heating them to melt temperature, so we get a kind of a homogeneous mixture, which can be one liquid or two liquid depending on range we are in, and it will form a combination of SiO2 plus calcium oxide, and it will form certain liquid, and we can cast it to form a glassy or polycrystalline microstructure. So depending upon how we are casting it, we can produce either a totally amorphous structure which is totally glassy in nature, or we can also induce some sort of a crystallinity to it by allowing certain nuclei to initiate before it really solidifies. So depending on how we are cooling it and what is the composition which is being involved out here, we can alter how the casting can result either amorphous structure or a totally crystalline structure. So that is the overall strategy with the casting. And again there is one more process for deposition, basically coatings, and that is called plasma spraying. And plasma, as we know, is the fourth state of matter. Herein it is utilized to basically let the powders through it, and it will melt it, and it will accelerate the powder particles so that they get impacted onto a substrate, and it tends to form basically coatings. And it is most widely used coating deposition technique for depositing hydroxyapatite, and it tends to develop something called lamellar structure. So we have powder which basically passes through some plasma plume, and then these particles are accelerated to certain velocities so that they get impacted onto a substrate to form splats, and consecutive layers basically tend to form layers over it, and this is called a splat structure or the lamellar structure. and it can also create certain porosity into it, because all the lamellae which we find here, they may not be intact homogeneous chemically to one another, they might be just mechanically integrated. So it can also create porosity if we can define certain way what is the overall initial powder particle size which we are trying to utilize, or even the kind of stand of distance from the plasma plume to the substrate. So there are certain parameters which we can really control and play around to render it a certain porosity on the coating material. And again here we can also have polycrystalline material which can be deposited using plasma spraying. So plasma spraying is one of the very important techniques which is most widely used for producing coatings onto implant materials, and it generally tends to result lamellar structure. It can also lead to producing some sort of a porosity onto the implant surface, because we can really control the powder size, we can control the heat basically by controlling the overall power which is being supplied to the plasma spraying unit, and that will eventually control the overall melting of the powder particles, and the impact of those powder particles onto the substrate will lead to the overall porosity in the microstructure. So in this particular manner, again we can control the cooling rate. So the cooling is typically very fast in plasma spraying, which is to the order of 10 to the power 6 kelvins per second. So by controlling the cooling as well, we can limit the solidification, or we can ease the solidification by preheating it. So those all are the things we can play around in terms of rendering a very dense structure or rendering a very porous structure. But ideally these plasma spray techniques are utilized for developing porous coatings for on the implants, and those coatings can be either polycrystalline, and they can even create porosity out here. So that is the overall strategy behind using a plasma spraying for the coating deposition. As we had seen earlier, that we can also provide some casting to get a particular shape, and the problem with the casting is once we are trying to cool the particular material in equilibrium, we get a very coarse material, the grain structure becomes very coarse. Though we will get some equilibrium crystalline phases, but the problem will be it will lead to very large shrinkage cavity, and once you have large shrinkage cavity, once we have very coarse grains, it will make the material very weak, and once the material has gone very weak, it will basically yield to the environmental attack. So that is a problem, that is the reason we don't want to really go with casting structure all the time. Though it can produce a good amount of it, we can really get a very good shape, or very good shape can be cast from it, but the equilibrium cooling is not really preferable for the cast structures, because first of all it will have very coarse grains. It will once we are heating it to very high temperatures and we are letting it cool according to the phase diagram, so that all the phases which are in equilibrium, they tend to equilibrate, but that equilibration will lead to much more coarsening of the grain. Though we will get equilibrium phases which should be present out there, but it will holding it for such long time at such high temperatures will basically make the structure very coarse. So once the microstructure is very coarse, it will lead to very huge grain sizes, and it will make the material very weak because of Hall patch relationship. And again this particular cooling will allow the phase transitions to occur, and also what will happen is that it will yield out to it will provide a very large shrinkage cavity in the center, because once the material is cooling down, it has to basically shrink, and that creates certain cavity, and that cavity generally is not acceptable because it will make the material very weak. And again once we have very huge grains, or once the material is very weak, it will obviously be prone to the environmental attack. So those are all are the limitations of the cast structure, that first of all it will make the grains very coarse, which will eventually germinate out of the equilibrium cooling. Once we have very coarse grains, it will lead to basically it will make the material very weak. Casting can also induce shrinkage cavities, and overall these things will make the material very prone for environmental attack. So those are the problems with the cast structure as such. So solution to that is we can go with something called liquid phase sintering. And in the liquid phase sintering, what we are doing here is, first of all we make a particular component, and that component is a green, and that is preformed into a desired shape. So we take a particular say maybe a particulate structure, and then we preform it to whatever kind of a shape we need. Say if we want to have a certain kind of a shape, we basically preform it to certain shape, while it retains around 10 to 40% of the porosity. So in this particular case, we are first preforming it into desired shape. So this is the desired shape, and this will still have 10 to 40% of porosity in it, and then we heat it to certain temperature so that one phase remains liquid. So if we go to a phase diagram, if we have particular material and we see a phase diagram for a binary system, then we will see in this one of the regions we have liquid, we have solid, we have alpha, we have beta. In this particular regime, we will have liquid plus alpha. So we will take the material to that particular regime where we have at least one phase which is liquid, and then we let it sinter. So what is happening out here, that we get all the particulates where one phase is liquid, that liquid will tend to go at the grain boundaries and it will basically draw the grains together by capillarity action. So we had say one grain, second grain, third grain like this, and everything else will be filled with certain liquid, and since liquid is filled all along aside it, it will basically tend to bring all the grains together. So this grain will try to go near to the other grains. So it will be more like this, that we have one grain, it will try to go towards the near second grain, this grain will also try to come closer to it, this grain will try to come closer to it, and this grain also will try to come closer to one another. So overall this effect arises because of the capillarity action. So because of capillarity, everything will tend to come closer and they will get basically consolidated, and it will lead to increased density among in the structure. So this is what is happening out here, that it will lead to increased density because of the capillarity action, because liquid is present at the grain boundaries which will tend to draw all the grains together, and that will basically make the structure highly dense, or it will increase the density out here. So but what happens in the liquid phase sintering is that since reaction is very slow, because in this particular case one phase is still solid, so it has to undergo much diffusion, and the prolonged holding at very high temperatures, it will basically lead that the overall structure becomes much more coarser. So in this particular case we have these particles which are still there. So in this particular case we had small grains which are present initially, and then one phase becomes more liquid. So in the overall structure, microstructure looks like that we have initial particles which were not melted at all, initial particles of one phase which were not melted, they remain as such, and again all the structure now, all the particles now they are now enclosed in a liquid phase. So that is what is happening out here, that everything is now enclosed in all these particles are now enclosed in a liquid phase. So liquid phase sintering, we are first of all we are taking the particular material or the component in the desired shape which still has certain porosity. Then we start the liquid phase sintering, in which we are taking a material to a temperature where we have at least one phase liquid, so that liquid tends to draw all the grains nearby itself because of the capillarity action, and once we have all the grains we allow the cooling to happen, and because of that the overall structure looks like that we have all the smaller grains which were nothing but the initial particles which did not melt at all, those are being basically covered with a liquid region, and upon solidification we see that kind of a microstructure which is kind of generated out here. So what happens that now all the liquid which is surrounding the particles, that can basically crystallize either into fine grains, or it can also, if in case we have some network formers which are present in the liquid regime, and those network formers are generally silica, they can retain the glassy nature. So we had liquid which are surrounding a smaller finer particles, and if we have much more of network formers which are present in the liquid regime, they can retain that particular structure, they can remain amorphous. So it will retain the liquidous nature of itself, and it can basically be again amorphous, and that process can occur when the liquid phase is basically quenched. So we see that the overall microstructure looks more like this. We have all the grains which are basically scattered out here and there, and then over that we have something, all the liquid which is basically covering it, covering all the grains which have basically made the grains come much closer to one another. So all this is basically liquid, and all these are the particles or finer grains which were not melted, and during the processing all the particles, all the grains, they have tried to come closer to one another. So in this particular case, so we can see that all the particles, all the grains, they have tried to come closer to one another as much as they could. So what is happening out here is that they have come as closer as possible. So in this particular case it has result densification. So we achieve the densification by the capillarity action, because of the liquid which is surrounding the particles. It has tried to bring all the grains to one another, and what happens in the next stage is that then happens that all this liquid is basically being surrounding all those grains or the particles which are unmelted. We can start seeing crystallization even in this regime, in the liquid regimes, or we can also see that the glassy nature or the liquid nature of this particular liquid remains as such. So from this liquid we can either get fine crystallites, or we can have again a liquid or a glassy structure. So that is what is happening in this liquid state sintering, that we are first of all we are heating it to a temperature where one of the phases is liquid, and then we are letting it cool, and depending on the cooling or kind of a composition of the liquid phase, we can allow the crystals to either nucleate, or we can also allow it to retain the liquid structure or the glassy structure at the room temperature. So that is what the overall microstructure comes out to be, that we have retention of the initial particles which were not melted, or the grains which were not melted, which is again surrounded by a glassy phase, or again a very fine crystallite phase, which basically develops from the liquid which was surrounding all those particles. And the next methodology of sintering is solid state sintering. So in this particular case, we can it can be utilized for producing very dense hydroxyapatite or aluminum oxide ceramics, and basically this solid state sintering happens because of the surface energy gradients, and in this particular case everything is in solid. So atoms, they basically diffuse along the contact areas which happen between the particles. So we take certain particles, and atomic diffusion along this particular regime on the surface as well as the lattice, along the lattice, it occurs because of the surface energy gradients. So they will tend to minimize their surface area. So we will see first of all kind of a necking which can occur between the two particles as the diffusion goes along at higher temperatures, and solid state sintering, we are not allowing any phase to reach a liquid regime. So the holding temperatures for solid state sintering are much lower than the liquid phase sintering. So that is one of the differences between the solid state sintering and the liquid state sintering, and in this particular case we only see atomic diffusion which is happening to cause the densification. And herein the material transport from one particle to another particle, it occurs via grain boundary diffusion, it can also be volume diffusion, or it can also be creep diffusion, depending on the kind of temperature this particular material is undergoing. So that is what the strategy out here is, that depending on the temperature we can either achieve a grain boundary diffusion, it can also be volume diffusion, or it can again be creep, which can occur to move the material from one location to another location for the mass transport. So again herein that sintering temperatures are in excess of 0.5 times the melting temperature, but again herein the lower temperatures and longer times are basically used when compared to the liquid phase sintering. So if we have used a particular cycle in which we have liquid phase sintering, the temperature regimes will be very high, but in this particular case this is for liquid phase sintering, but for solid state sintering we can go to very low temperatures, but we can keep it for prolonged heating. So we have solid state sintering which will progress like this. So that is, this is with respect to time, this is with respect to the temperature. So this is kind of a difference we will see in terms of liquid phase sintering LPS or the solid state sintering which is SSS. So in this particular case we can make very dense structures, but we do not allow any of the phase to basically become liquid, and because of surface energy gradients we can first of all allow a contact, particle to particle contact, it will start create a neck, and once we have the surface diffusion then the volume diffusion can also occur, and depending on the temperature we can also have creep coming into the play for the overall mass transport of the material. And sintering temperatures generally in the order of 0.5 Tm, more than 0.5 Tm, but these temperatures are lesser than that of a liquid phase sintering, because depending on the phase diagram we are not allowing the structure to undergo to form a liquid phase, and in this particular case we are holding them for much lower temperatures but for much longer times and when compared to that of a liquid state sintered region. So one more difference which comes out eventually is, because if we have a liquid present in the material, it will tend to draw all the grains closer to itself, that will lead to much more densification as well. So overall densities in the solid state sintering are much lower as compared to that of a liquid phase sintering as well. So that there are certain differences which can arise in solid state sintering and the liquid phase sintering. So in this particular case we see that the crystals, they are bonded via sintering, and it can also tend to close the channels which were open earlier during when the heat treatment is being given to it. But in this case we are holding them for much lower temperatures, so that can lead to very fine grained microstructure. And one more thing important here is it can also result high purity, because we are not allowing a solid to become liquid, and since liquid have much more higher capability to dissolve certain impurities into it, and those impurities basically are now entrapped into the material in case of liquid phase sintering. But since here we are not allowing any liquid to form, the material tends to be much more purer than as compared to the liquid phase sintering. At the same time, since the temperature is much lower, we can also get very fine grained microstructure. So in case of liquid phase sintering, we will see kind of a microstructure which is very dense, and it has entrapped liquid in between out here. But in the solid state sintering, we will see all the particles which have come together because of the mere contact difference in the surface energy and the contact between the particles. So we will get a dense structure, but not as dense as liquid phase sintered region. So in this case of solid state sintering, we will see all the particles which have come closer, and also they will have some sort of a surface melting because of the surface contours of the kind of a curvature. Surface can melt to a certain extent, but not it will be very marginal, and then it will basically contact with the nearby particle, and then volume diffusion and surface diffusion, because of those it will create the bond with the nearby particles. But it cannot eliminate all the porosity, the solid state sintering, because we need very high pressures at very high temperatures to eliminate that porosity. So material has to deform, the material has to yield to be able to result that kind of a densification, which is so easily possible in the liquid phase sintered region, because for liquid it's very easy for them to flow through the channels, through the pores, to create that kind of a densification. So liquid tend to take all the empty spaces directly, but it becomes very difficult in case of solid state sintering. So that is all the difference between the microstructures of liquid phase sintered structure in the solid state sintered region. But SSS or the solid state sintered material, they tend to be much more purer, and they tend to be much more fine grained, because the temperatures are very low as compared to the liquid phase sintered structures. And also we can see that there can be some formation of glass ceramic. So this type of material can form once we can have initial material which is a glassy, but the end product which comes out is more or less a ceramic phase. So how we can produce that particular structure is that in the first step we make a total melt. It means we make it a glassy. So first of all we are taking the material to a higher temperature, then we are quenching it to form a glass. So first step is that we form a glass, and the second step becomes that we heat treat them at around 500 to 700 degrees centigrade to nucleate certain crystals. So first step we make a glass, then we take it to a temperature where it can nucleate certain crystals. Once it has initiated some number of crystals, then we can basically heat it at much higher temperature, so that all the nuclei which are present, they can basically grow, and once they start growing, they will start impinging upon one another. So now we have gotten a composite which is a glass ceramic. So in this particular case we are starting with a glass, and then first of all we are melting everything, and then we are quenching it to result a glass. So once we have a glass, then we basically are heating it up to around 500 to 700 degrees centigrade to nucleate certain crystals, and we are allowing it to grow at much higher temperatures, 600 to 900 degrees centigrade. And once the crystals start growing, they will tend to impinge upon one another to form a ceramic. So that's what we can see, that in our initial condition we had a glass. So glass was basically formed by melting and followed by consequent quenching. Then we let the glass to start nucleating certain crystals. So we heat it up to maybe 500 to 700 degrees centigrade, so that nuclei can basically form, and those nuclei tend to become crystals, and then crystals starts to become a little bigger grains. Once we again heat it to a much higher temperature, which can range from 600 to 900 degrees centigrade, and once enough nuclei are present, they will eventually grow to impinge upon one another to form a polycrystalline material, which is again nothing but a ceramic. So in this particular case we can get a non-porous microstructure, and in this particular case we can get grains which are very fine. At the same time they are randomly oriented, because in this particular case we had a liquid and there was no particular location where the grains will basically nuclei, they tend to get nucleated at random locations, and that is the reason they are also randomly oriented as well. And then what we get, that the residual glassy matrix can also be present, because it might lead to that certain regimes they do not get chance to nucleate at all, and even raising them to very high temperatures we may not see any formation of any crystals or nuclei at those certain locations. So we can also see retention of a glassy matrix in the microstructure. So this can also result that we have some residual phases of glass inside the microstructure. Eventually we can also form glass in glass matrix as well, if we can find there is some phase separation which can occur at much higher temperature. So let us go back to the phase diagram, that in the phase diagram we have kind of two phase material. So it can lead to formation of certain glassy phases or immiscibility gap between the materials. So if we had say liquid 1 plus liquid 2, so in this case we had liquid 1 plus liquid 2, and if we are basically cooling it down from that particular location where we had liquid 1 and liquid 2, so we can see that liquid 1 will tend to remain liquid 1, L2 will be able to remain liquid 2, because we will have basically if we can quench them at such faster rates that liquid 1 does not get time to equilibrate with liquid 2, and they do not really tend to form one homogeneous liquid. So in that particular case we can get a glass in glass matrix as well, when we have a non-miscible liquid which can form at much higher temperature. But again this can lead to very complex microstructures, because if once we try to heat treat them or something like that, it can even lead to very complex microstructure. So I will basically take a break here. We can see that we can have a variety of microstructure which can generate depending on the processing technique. So we can either have a glassy kind of a structure, we can also have a kind of a cast structure, we can also have plasma sprayed structure, we can also have a kind of a solid state centered ceramic, we can also have liquid phase centered ceramic, or we can also have a kind of a polycrystalline matrix which can be again ceramic in glass, or it can be also in glass. So there are various kind of microstructures which we can really attain just by varying the processing technique, and all these are basically thermal spraying techniques. So depending on what kind of a structure we are looking at, whether it is glassy or whether it is a cast structure, whether it is a plasma sprayed structure, we have to play along with the temperature and time cycle of the processing, in which we can alter the various properties which can germinate out of the particular processing technique. So in this particular case we can draw a kind of a time temperature graph. So if we have time out here and we have temperature out here, so in case of if you want to attain a glassy structure, you basically heat them to very high temperatures, much above the melting temperature. So if we have a melting temperature somewhere here, we will take the particular material at very high temperatures and will basically quench it. So that quenching will lead to retain the glassy phases, or the overall structure will remain amorphous. So we will attain something called a glassy structure out here. And in second case we can also have a cast structure. So cast structure also we basically take it to very high temperatures, we will put it in a mold and then we let it basically cool in the mold. So that kind of a thing will it comes eventually via homogenization. So we take it to high temperatures, let it homogenize for some time, and then basically we cool it down to room temperature. So this in this case of casting we can also get some sort of a microstructure. But the problem with casting is we can get very coarse grains, and once we have very coarse grains we can also get deterioration in the properties, all the mechanical properties. We can also see sometimes the shrinkage cavities, which will again deteriorate the properties of material and it will lead to the environmental degradation. And in third case we can also get something called a plasma sprayed structure. So in this particular case we can see that the structure is much more polycrystalline in nature. So in this particular case we are taking the powder particles, we are getting them heated through plasma, which is nothing but an ionized gas, and we let the particles flow through that particular plasma and they are accelerated to very high velocities, and while they are experiencing very high temperatures which can exceed even 10,000 Kelvin, they are basically impacting the substrate material. And depending on the powder size, depending on the power which we are utilizing for plasma spraying, we can attain different kind of porosities as well. So plasma spraying is basically utilized for depositing some sort of a ceramic coating onto an implant surface. So that is the overall idea behind it, and in that particular case we are able to reach very high temperatures, and the cooling rates are very drastic. They can, in plasma spraying, temperatures can be as high as 10,000 Kelvin, and time can be less than couple of minutes. So cooling rate can be as high as 10 to the power 6 kelvins per second. So few seconds to minutes will be able to complete the plasma deposition process. And coming on to third property, let us say a liquid phase sintering. We are taking the material to below the melting point, but at temperature where we can have formation of at least one phase which is liquid. So we take it to a certain temperature which is again a liquid, and then we hold it for certain duration, and then we let it basically cool. So this is liquid phase sintering, and in liquid phase sintering, what is happening is we are allowing one phase to reach, one phase to become solid, one phase to become liquid, and because of capillarity now, that liquid tends to basically bring out or draw all the grains together, and that basically is consolidating the material. So what we are seeing, we will have some locations or some grains which are unmelted, and those are now being clogged in by liquid phase, and that liquid phase again we can have, depending on the kind of composition, we can either get a crystallite matrix, or we can also get a glassy matrix depending on what kind of structure we want. So if we cool it very rapidly, and if we have network formers such as silica, they can basically make the overall matrix very glassy in nature. That is the liquid phase sintering. Again, we can also go to solid state sintering, in which we can hold it to a much lower temperature as compared to liquid phase sintering, but for very longer times. So we can get again a very dense structure. But now in this case, when we have solid state sintering, we basically get very fine microstructure, because the temperature is very low as compared to liquid phase sintering. So solid state sintered regions, they are much denser in nature. Also, we are avoiding the formation of any liquid phase, and liquid phase have the tendency to absorb some impurities which can arise from either the mold wall or somewhere else. So ideally, the solid state sintered products are much more purer than the liquid phase sintered products. At the same time, they have the solid state sintered component will have much higher porosity also as compared to the liquid phase porosity, because there is no more liquid which can flow into the crevices or any cavities to draw the grains closer. So here we need to apply certain sort of a pressure or some sort of a hydrostatic pressure to basically consolidate the overall structure. And in this case, we only have solid state movement of the solid state diffusion processes, such as which can arise from either surface diffusion or volume diffusion or the lattice diffusion, or it can also be creep depending on the temperature we are utilizing out here. So that is the again advantage with the solid state sintering process. So sometimes even getting a porosity also becomes much more advantageous in case of solid state sintering, because we really need the porosity so that cells can come and they can attach themselves onto the particular porous surface. So sometimes this solid state sintering is much more preferred technique to make a particular component. And finally, we can also make a particular material which can have much more of a ceramic in glass or glass in glass. So we can have ceramic in glass, or we can also have glass in glass structure. So coming to the first ceramic in glass, we can first of all we can quench the material. So first of all, we have a particular material, we take it to melting point, and then we basically quench it. So once we quench it, we will get a glassy phase. So once we have a glassy phase, now we increase the temperature to certain regime. So first of all, we do a quenching. So once we attain the glass out here, then we basically heat it again to certain temperature, which can range from 500 to 700 degrees centigrade. And then once we have this particular temperature, the nucleus starts forming out here. And once the nuclei have already formed, we can make the crystals grow by heating at even much higher temperature. So 600 to 900 degrees centigrade, we can let the nuclei grow at much higher temperatures. And then basically if we can let it cool down, then basically what we have gotten is ceramic in glass, because the overall matrix can again still be glassy depending on the way we cool it, but most of the nucleus already formed. If the nucleus formed completely, we can get a polycrystalline matrix, and so we get all the grains which are very fine, and everything is much more crystalline or ceramic. But it can again be glass in glass. So once we have cooled it, depending on the way we are cooling it, we can again retain the glassy phase itself. Once we have much more of a network former in the liquid regime, we can retain the glassy structure itself. Once we have two liquid which are forming at much higher temperatures. So, for glass and glass, we need to have a phase diagram where we can see two regimes which are forming, liquid 1 and liquid 2 at very high temperature. So, we have immiscible liquids at high temperatures. So, as temperature is very high, but much below the melting point, overall total melting point, we will see liquid 1 plus liquid 2. So, in that particular case, we are seeing a phase diagram which will have liquid 1 plus liquid 2 in this particular regime, and then they basically tend to homogenize at much lower temperatures, but we do not let them homogenize at lower temperature, we basically quench them from the immiscible regime. So, in this particular temperature, we basically tend to quench them. So, we can get two liquids as it is, as they are in the liquid phase. So, we do not let them to homogenize at lower temperatures, and we basically retain the structure of liquid 1 and liquid 2 which were immiscible at much higher temperatures, and then we get glass in glass. So, these are the various comparison of the various thermal processing techniques to get very different microstructures, which can be glassy, which can be a cast structure, which can be again a plasma spread structure, which can be solid state centered region, which can be again liquid phase centered type of microstructure. It can be again polycrystalline, it can be ceramic in glass, it can be glass in glass. So, this is the overall mixture or a blend of different techniques, and which can really help us provide a very different paradigm of properties as such, or different type of applicability in terms of the microstructure which we can get out of it. So, there can also be mechanical processing. Apart from thermal routes, we can also have mechanical routes to basically produce a glass ceramic kind of a composite. In this particular case, we take a ceramic powder and we take a glass mix, and then we basically compress them all together. So, we see all the powder particles which are basically thrown here and there, and then the glassy phase which basically flows over those particulates to form a matrix. So, we have, so in this particular case, we have all the particles, solid ceramic particles, and then we have a glassy phase which is basically covering the entire regime, and then we basically compress it or mechanically press it, so that we can get a structure something like this, that it has a particulates which has a surrounding liquid or a glassy matrix. So, that produces a glass ceramic composite. So, that is what we are able to see out here, that we can get various kind of techniques for processing the ceramic, bioceramic or a bioglass or a glass kind of a composition, either via casting or via sintering, which can be liquid phase sintering or it can be solid state sintering. It can again be plasma spraying. So, basically thermal treatments are utilized in this particular case, and it can again be more mechanical pressing as well to yield a certain microstructure. So, overall what we basically see in this particular lecture is that we can utilize the either thermal spraying the thermal techniques or a mechanical techniques to form a bioceramic or a glass kind of a microstructure. So, in thermal techniques we can get various type of microstructures which can be resulted. They can range from either cast structure, which can be plasma spread structure, which can be glassy structure, glass and ceramic structure, liquid phase sintered structures, solid state sintered structures. So, the variety of all these structures can be resulted from a different type of techniques which are utilized here. So, for attaining a glassy structure, we take the melt to a very high temperature and we cool it very rapidly, or we can also induce some sort of a network formers and network modifiers. So, we can get a combination of silica, which is a network former, and we can have a network modifier of calcium oxide to result overall a glassy structure. We can also get a cast structure by taking the melt to a high temperature and letting it cool in a cast product. But here the problem is to produce an equilibrium structure, the overall grain growth really occurs during this particular time, and because of that there is much deterioration of the properties, the mechanical properties, and also it can lead to deterioration of the corrosion properties, because now the overall structure is very weak. It can also lead to some cavity formation which can arise from the shrinkage of the material. So, that is a problem with the cast structure. We can also go with the liquid phase centered structure, in which we take the temperature to such that we have one phase which forms a liquid, and second phase remains as such unmelted. So, we have the liquid phase basically collecting or drawing all the other grains closer to itself, and it forms a very dense structure. But the overall temperature is very higher as compared to the solid state sintering, wherein we do not make even one phase go to a liquid regime. So, we have solid and solid, and then we basically are sintering them, and there is a transformation of material via solid state diffusion processes, which can be either grain boundary diffusion or lattice diffusion, or it can be even eventually creep as well, depending on the temperature we are utilizing. But herein we see that since everything is solid, there is no much impurity incorporation out here, because the liquid tends to attract or dissolve much more impurities. It can be in the gaseous form, it can be arising from the surface of the overall cavity. So it can arise from there as well. So in this solid state centered structure, we can see the grains are much more finer, because here we are keeping the material to be much at lower temperatures as compared to the liquid phase centered regime. And again, we can also process the material via plasma spraying, where we are taking the material to very high temperatures and we have very high cooling rates. So they basically form as splats or lamellae onto a substrate, implant substrate. So we can get a polycrystalline matrix as well, or eventually we can also form something called glass and ceramic, ceramic and glass, or glass and glass kind of composites. So here we first form a glass. So in this particular case, we take the material to a very high temperature, we quench it so that we get a glass, and now we have to crystallize this particular glass to achieve ceramic in the glassy phase. So we take it to higher temperatures, where we can maybe around 500 to 700 degrees centigrade, where we can let the crystallites get nucleated out here. Once they are nucleated, we can increase it to further higher temperatures, order of 700 to 900 degrees centigrade, wherein all these crystallites tend to grow, and once they are growing, they will start impinging on one another, and depending on cooling, we can either achieve a polycrystalline matrix, or we can also achieve a glassy matrix. So that becomes a ceramic in glass. We can also get glass in glass by basically having a microstructure where we have two immiscible liquids at higher temperatures. So we have liquid 1 and liquid 2, which are immiscible. Once we take them to lower temperatures, they tend to get miscible, much at lower temperatures. But what we do, we take them to the temperature regime where we have liquid 1 plus liquid 2, and we cool it very rapidly. So what happens, that liquid 1 remains as such at the room temperature, liquid 2 also remains as such at the room temperature, and we get glass in glass matrix. Those are all the thermal techniques. And coming to the mechanical techniques, we can take a ceramic material and we can get a glassy phase. We just basically mechanically press them together. So what we are getting eventually is, we get solid particles which are ceramic, and those are basically being compressed via glassy matrix, because for the glassy phase, it is easier for them to flow around and consolidate the overall material. So this is what basically completes the overall processing of bioceramics or glasses in this particular lecture. Thanks a lot.